Okay, so this is a rather general talk in the first half at least about methods of effective theories. And of course there's a well-established framework for calculating low energy effective actions and so on. But that's really works well when we have a canonical theory. And for quantum gravity that's not always realized, so that's just one of the issues which one has to at least generalize and perhaps address. We have to find a good canonical formulation for effective systems. The meaning of low energy, or anything related to energy, is never so clear in gravity where there's no local energy concept. And the Hamiltonian is unbounded from below, so we can't use the vacuum or ground state as a means to tell whether we are at low energies. And that's also a problem when we have to select suitable states or theories. And then finally, and that's what I'll talk about in more detail in the second half of this talk, when we quantize gravity, we quantize space-time as well. And that means its symmetries, covariance, have to be derived from the theory. We cannot presuppose them, but usually when we write down effective actions, we start with an idea about the symmetries to tell us what the terms are that should be included. So if those theories are not there in the first place, we have to really generalize the framework. So again, it's slightly more general in this talk, so I'll talk about the framework and some results. Something that has recently become of some interest also in this setting is non-associative algebras of observables, so there are not many methods in this case. I'll talk a little bit about this. I mentioned the vacuum, so in this canonical setting we do not need a vacuum state to expand the theory or define an effective action. But then there's more freedom, because if there's no vacuum, then there's no substitute state which is as nearly distinguished as the vacuum state. So in this context, the role of symmetries is weaker, because there's no vacuum. Then even if the theory has symmetries, the state probably breaks some of them, and then the corresponding effective Hamiltonian or action does not have the same symmetries. But then when it comes to gravity, the roles of symmetries comes back, because in this case all the symmetries of space-time are really gauge transformations, and they have to be there. They should not be broken. So in this case, the roles of symmetries are stronger, but then we come into this issue of quantizing space-time and covariance, so they may not be the symmetries that we know from classical systems. And there have recently been some surprises related to this issue, because we come up with new space-time structures as we derive effective systems. One crucial thing is signature change, so that's one of the issues I'll talk about in more detail. And applications to cosmology, I think Aurelian already talked about this maybe yesterday. I'll mention it briefly and then conclude with remarks on black holes in this signature change setting. So the setup is, the starting point at least, is pretty simple quantum mechanics. So it's an extension of Ehrenfest's equations, which tell us how expectation values evolve. But then if one writes down these equations, and if we really want to turn this into a closed set of differential equations, then on the right-hand side, an expansion of the force expectation value brings in quantum fluctuations and higher moments. And they're dynamical as well. So we get a really large set of equations, usually infinitely many ones, coupling all these, well, the expectation values first of all, but then all kinds of moments. So that's where we need a more general formulation to handle all these equations. So again, these are the variables, expectation values and moments, totally symmetrically ordered. It's useful to introduce some kind of geometry, turn this into a phase space using a Poisson bracket based on commutators, so that's not the classical Poisson bracket. And then what we usually use as operators, like Hamiltonians or constraints if we have gauge theories, their expectation values can be expanded in terms of these variables. Well, that's illustrated here. We just rewrite it identically and then do a formal expansion in these operators minus their expectation values. So in this way we can write the expectation value as a function on this phase space. Using these Poisson brackets here, we generate we generate equations of motion, or for constraints, gauge transformations. I'm sorry? Oh, yeah, if you have Q and P, then of course the ordering is not unique, so we use a totally symmetric or Weil ordering, which means you sum over all permutations, divide by n factorial. So that's a choice. It's not really required, but just to avoid overcounting, you have to select one. That's pretty convenient usually. So for instance, if you use this ordering, then expectation values, an expectation value and a moment have a zero Poisson bracket. If you choose a different ordering, that's not necessarily true. So it's more for convenience at this point. So the Hamiltonian then generates equations of motion. Here's one example for an anharmonic oscillator. So they get really long. It's not really complete here, not even complete. And it's infinitely many ones. So that's usually not a good idea, but if you use approximations, semi-classical expansions remove a lot of equations to fixed order in H bar. And if one combines this with an adiabatic approximation, assuming that the moments vary slowly compared with expectation values, one can solve these equations into second adiabatic order, first order in H bar. The previous equations are equivalent to this one here, second order differential equation for Q, still the expectation value. And that's just the equation of motion generated by the usual low energy effective action. So it's the same equation, the same dynamics, but fully canonical. One can address the vacuum or ground state in quantum mechanics. So that's, well, just a simple example, harmonic oscillator. The Hamiltonian, again, we take the expectation value, write it in terms of moments, using the previous expansion, or second order, it's even easier. You just write these fluctuations as operator squared expectation value minus expectation value squared, and that's an identity, so there's no formal expansion at this point. So here, these are at this level 4 independent variables, two expectation values, 2 moments, fluctuations. But if we use our equations of motion from the previous slides for zero anharmonicity, solve them for stationary state, so moments constant in time, and saturate the uncertainty relation, and these 2 moments fluctuations are fully determined, and the combination gives us just the 0-point energy. So we get the correct effective potential, in this case just a constant, but it works equally well if there's an anharmonicity, so one can derive a low energy effective potential, and even when these canonical methods are applied to quantum field theories, in which case one can rederive the Coleman-Weinberg potential. So again, everything re-derived, but by telling us which equations we are using, it tells us how we can generalize the framework. If we drop some of the conditions, we get a more general system of equations, but then also we're not so sensitive to specific vacuum choices. Here's just one example, which is no longer harmonic, so it gets more complicated, but things can still be derived. It might even have an advantage for standard QFTs. We're still working on some computational schemes because we're not computing complicated integrals. We don't really need any specific tricks. But computationally, we get large systems of linear and quadratic equations, which can probably be handled, but it needs some work. There might be some advantage here, but we're not sure yet. In any case, in this way, one can relax some of the conditions, address the vacuum. I switched to a slightly, back to the general setting. So we used these equations in this Ehrenfest form. Now these work much more generally because we just need an expectation value functional. We don't need wave functions or Hilbert spaces. Oh yeah. In some cases it does. If you use this H-bar expansion, it doesn't, but the H-bar expansion is not the only way to decouple these infinitely many equations. So there are some other examples. If you're close to an integrable system, then you can use some of the symmetries to decouple these equations and get non-perturbative results. It's not as common, of course. That's a more special situation, but it is possible. So then for this equation, we don't need wave functions, so it's sufficient to just have this expectation value functional, and then all the equations and the moments, the variables are still defined as before. So several consequences, it includes mixed states, so we can compute expectation values from mixed states, and they are concluded in this dynamics here. It's a similar picture as in algebraic quantum field theory, so related advantages then. And in quantum gravity, and again that's something I just mentioned here, it's useful in the context of the problem of time because we don't require wave functions or Hilbert spaces. We don't have to compute physical Hilbert spaces, which is usually a very difficult problem when there's no global internal time. So here that probably has some advantages, but also that's still being worked out. And then the thing I mentioned here, the algebra might be non-associative, so one can still define expectation value functionals on these issues, on these objects. But one could not represent them on a Hilbert space because that would automatically imply that the operators are associative, so that's not consistent if the observables are not associative before we start quantizing it. It's not a very common situation, but it appears in a few cases. The oldest example is magnetic monopoles. So in this case, if we do not have magnetic monopoles, we have a vector potential and this canonical momentum. But for the just kinematical momentum, so mass times velocity, it implies a non-canonical Poisson bracket. If there's no vector potential, so if we do have magnetic monopoles, this Poisson bracket is twisted, so it's a generalized version. It means it's the Jacobi identity is no longer satisfied. And the violation is proportional to the divergence of B, or the monopole density. When we quantize using, well, the usual trick, turning Poisson brackets into commutators, that implies non-associativity. Another example is chiral anomalies in some quantum field theories. They can lead to non-associative current algebras. And more recently, double field theory, some off-shell version of string theory, leads to non-associative structures. So there's some applications, not really crucial examples, but interesting ones. And so the question is how one can quantize in this context in which a Hilbert space representation cannot exist. And there are two approaches. The first one is using star product deformation quantization techniques. And that's been worked out for this monopole example, which is very closely related to the double field theory one, some toy models at least. And the alternative approach would use canonical effective theory. So we would just use states on the algebra as positive linear functionals, and then we can still work out these equations of motion and related dynamical properties. There's still some open questions. So these functionals are not arbitrary. They have positivity conditions, which are related to uncertainty relations. So the existence of sufficiently many of these positive functionals on a non-associated algebra is not clear yet. One cannot use the GNS construction, so usually if we have an associative algebra, if we know just one positive state, we can use the GNS construction to generate a full Hilbert space, which comes with all the positive states we need. But the GNS construction works only if we have an associative algebra. So that route is not open, and people are still working on alternatives. Possible relations. So I mentioned the Jacobiator. It does not uniquely imply an associator, so there are some choices. The simplest case would be an alternative algebra in which the associator defined here would be totally antisymmetric. And that's been used in these canonical effective calculations recently because it simplified some of these commutators that we need for Poisson brackets. And some time ago also for an axiomatic setting of non-associative quantum mechanics. But it turns out that this condition may not always be realizable. It's a choice which we can make for basic operators, just for the momenta, for instance. But then for arbitrary operators, like products of momentum components, it's not so clear. We have to worry more about relations in the algebra. And this star product here does not lead to an alternative version, and it seems possible to prove that it's never that we can never have an alternative algebra in this setting. So I would have to rethink the axioms and some calculational methods. And the final question, eigenvalues and eigenstates, even the definition is not clear if we do not have an operator representation. So this concludes this more general part. So we're still looking for possible applications. That's why I wanted to present a more general perspective first. Yeah. Which sixth term? I'm sorry. Oh. I'm not sure. The example which breaks alternativity is something like px squared, py squared, pz squared. So if you put, yeah. So if you get to a product of momentum components, so px, py, pz is easily totally antisymmetric. But if you have products of composite operators, it's more complicated. The axioms? It depends on what you mean by a rule. So you can yeah, I mean, there's some that refer to the measurement problem, some that refer just to the dynamics. We do not have a Hilbert space. If you have a Hilbert space, anything you represent on a Hilbert space is associative. That doesn't work anymore. Yes. But it's still within the setting of algebraic quantum mechanics. Maybe we can also discuss in private. But the so this algebraic setting. Something has to, well, yeah, the standard way you teach it, but it's we do not modify anything that people would use in algebraic quantum field theory, for instance, where they also work with functionals on local algebras, and they do not necessarily worry about Hilbert space representations. So you can still do quantum mechanics. That's not necessarily the simplest way that you would use for teaching. But at this level, so you have certain positivity conditions on your functionals, and that's sufficient to make sure they are good states. You have uncertainty relations and so on. And you define the dynamics in this way. That's still possible. So anything you do before you do a measurement does not need to be generalized. For measurements, one has to worry about these axioms. Yes. Well, it's related to this last question. I mean, you cannot use, if we do not know how to define eigenstates and eigenvalues, you cannot talk about measurements in the same way. I think the main open question is how to come up with good axioms for the measurement problem. Anything else, just evolving a wave function, is it's a generalization, but it's not very strong. It's 3 examples. There may be more, but these are just some situations in which non-associative algebras come up. So if you want to quantize them, they are maybe kind of exotic, magnetic monopoles, but people are constructing condensed matter analog systems, so it could be applied in this case, even if we do not have fundamental magnetic monopoles. Chiral anomalies, there's some chiral QFTs, which give rise to non-associative current algebra. So depending on how you quantize them, you have to address the issue of how to turn this into an algebra or states on an algebra. And then with double field theory, I'm not an expert on this, but it appears only when in an off-shell formulation. So I think people, even within this community, are somewhat divided about whether it's necessary or not, because it's off-shell. And as soon as you go on-shell, the associator goes to 0. But it's a mathematical example, at least. And there are chiral formulations of gravity coupled to fermions, so it might even be necessary for quantum gravity, depending on what kind of matter you couple to it. So, and at least mathematically, it's been discussed for a few decades, so that's also at least one reason to think about it. So, if anyone is interested, I'd be happy to talk about it in private, but now, the more specific quantum gravity topic is about space-time structures. So if we do perturbation theory on space-time to get some cosmological effects, for instance, then classically we have two equivalent methods. So we have general covariance, which gives us transformations between the modes, corresponding gauge transformations, and they could be implemented by using gauge invariant combinations, for instance. Or we can just fix the gauge classically and then put everything in the setting of a standard field theory on the background. So these two approaches are equivalent classically. But then when we try to quantize it, this crucial feature of general relativity comes up here. Gauge transformations and the dynamics are closely related. They are generated by the same objects. And they are related to space-time structure because the gauge transformations just tell us how we deform spatial hypersurfaces in space-time. So when we quantize, then these two strategies might lead to different results. In quantum gravity, we would usually try to quantize anything the theory gives us, which means these constraints if it's a canonical approach. We do expect quantum corrections in the dynamics, higher curvature terms, perhaps something else. But if the dynamics and gauge transformations come from the same fundamental object, then gauge transformations should have quantum corrections as well, which means that the spacetime structure might be modified. So that brings us back to the question I posed on the first slide. Any kind of quantization of gravity, depending on how we do it, might give rise to modified spacetime structures. If we fix the gauge before we quantize, it's a different approach. It's just ordinary quantum field theory on the background. And we would have to presuppose what kind of spacetime structure we have, which is, it might not be an explicit statement, but it would be contained in these gauge fixing assumptions. So these two strategies can lead to very different outcomes, and in the rest of this talk I'll present an example related to loop quantum gravity. So in this approach, there are additional modifications, not just higher curvature terms. Again, Aurélien might have talked about this, but here's just a very brief review of one of the effects that people find interesting. So just isotropic models, you have the Friedmann equation. What we usually expect is a higher curvature expansion on the right-hand side. So we get higher powers of the Hubble parameter h and higher derivatives as well, some covariant combination, or which would be covariant when it's embedded in an inhomogeneous setting. In loop quantum cosmology, that might also come up, but there's a second kind of quantization which replaces the Hubble parameter squared by a periodic function like this, because the theory represents only holonomies or matrix elements of SU2 holonomies, but not curvature components directly. So that's often used as a modification or some kind of regularization to represent the dynamical constraints of Friedmann equations on the Hilbert space of loop quantum gravity or loop quantum cosmology. So there's a modification even before we introduce higher curvature that can also be expanded, but it does not give rise to these higher derivative terms. So it's even in this expansion, it appears slightly different. It can be turned into this equation here, so that's just reformulation using canonical relationships between the variables. And the interesting effect, which has been studied a lot, is the fact that this the right-hand side can be 0 when the density is close to this quantum gravity scale, which might be the Planck density. So L is a length parameter appearing in this function here. If L is the Planck length, this is the density is the Planck density. So when we're close to this density, H can be very small or 0, which suggests a turning point of the scale factor, usually a minimum, so that gives rise to bounce models. The question is whether that can be part of a covariant theory, which is modifying an isotropic equation, doesn't tell us much about how space derivatives are related to time derivatives. And it doesn't tell us much about how we evolve inhomogeneity. So we could use this as a background and then quantize mode equations on this background, but that would be this quantum field theory on curved spacetime, modified spacetime approach I had on the previous slide. That's not necessarily quantum gravity. If we go in more details here, we'll see that there's a difference between these two approaches. Don't have a lot of time left, so I might be a little bit fast on these technical slides here, but the main issue is the old anomaly problem of gravity. So the constraints form a complicated set of Poisson brackets with structure functions, so these f, I, j, k are phase space functions, which means if they're quantized, they will be operators, but then, as Koba noticed in the 60s or 70s, there's several problems related to this, because if they don't commute, then the right-hand side is not symmetric, so the constrained operators cannot be symmetric themselves, which gives rise to technical difficulties, maybe even more severe ones. So that's one of the old problems, which hasn't been fully resolved, also in loop quantum gravity. But in this effective approach, one can solve it, but at least one can circumvent these problems. So in the effective approach, constrained operators are replaced by expectation values. Now, a 0 expectation value doesn't imply that the operator is 0, but if we combine the expectation value of the constraints with these objects, so all polynomials in basic operators times the constrained operators, if these expectation values are 0, we have a complete set of constraints on our quantum phase space. And with these products here in this specific ordering, so there's no symmetric ordering at this stage, the expectation values may well be complex. So there's no problem with non-symmetric constraints, because we're dealing with complex expectation values anyway. One can show that this set is first class if the operators are first class, so consistent gauge transformations. And then I'm just mentioning this briefly here. So the classical structure functions, it turns out, are usually not quantum corrected, because all quantum corrections would go in higher curvature, in higher coupling terms, where lower order constraints with low order polynomials couple to higher order polynomial constraints. But the classical structure functions are usually just evaluated in expectation values, no quantum fluctuations, no other corrections. So if we apply this to loop quantum cosmology, hasn't been fully done in this setting, so moments haven't been fully included. But because there are these holonomy modifications, there are corrections in the algebra and the structure functions, even if we do not include all the moments. They usually look like this. So that's the most important part of the algebra. So it tells us how two spatial slices are deformed along their normals, and the commutator is usually a spatial translation. So that's contained in this Poisson relationship. It's classical if beta is equal to 1, so then we just have the classical spacetime structure. But with these holonomy modifications, first done in isotropic models, and then one tries to embed this in inhomogeneous settings, the coefficient usually cannot be equal to 1. It's related to the second derivative of this modification function. So it's still fully determined. So once we choose our modification, the algebra here, the kind of gauge transformations, corresponding space-time structure is fully determined. But it's not classical because the second derivative with this sine function, for instance, here is not constant. So in the canonical setting, we still have a well-defined effective space-time structure. It's not necessarily Riemannian because this coefficient is not equal to 1. Sometimes there are field redefinitions to bring it back to Riemannian, and not with the initial effective metric, but a modified version. But it's a more general space-time structure. The main physical result is signature change. So the cosine function is not positive definite, and more generally, whenever we have a function f with a local maximum, so anything that gives us a bounded density in this modified Friedmann equation, anything of this form gives a negative beta around the maximum, and a negative beta in here is, well, if beta is exactly -1, that's what we obtain for Euclideans, 4-dimensional Euclidean space instead of Lorentzian space-time. So a change of sign of beta implies signature change, which one can also see in a field equation. So they typically look like this. There might be source terms, other terms. But if you use your modified canonical system with this beta in it, you can derive field equations using canonical equations of motion, and beta appears in the spatial derivative term. So it's a mixed type differential equation, which means it would have initial value problems while posed if beta is positive, but 4-dimensional boundary problems when beta is negative. So now that's something which mathematicians have studied, starting with Tricomi 1930s. So one can combine initial and boundary value problems in this characteristic way here. So so that illustrates this bounce model. So that would be the Euclidean part, and then 2 Lorentzian phases next to it. In a Lorentzian phase, we can replace the standard initial conditions by a characteristic problem, meaning initial values on a light cone. And the light cone can be connected smoothly with an arc like this in the elliptic phase. Now if we impose boundary problems only on one of these light rays here, so not on the full light cone, but just half of it, and on this elliptic arc, it turns out it's a well-posed mix of initial and boundary value problems. So initial values, or values of our function u here on this line, give us a unique solution in the interior, and depends smoothly on the initial values and so on. But to do this, we need future data. So we cannot start in the infinite past or well before the signature change happened. We always need something which connects into the Euclidean phase, so some part of future data. Something related to it, they're usually poles, so at this endpoint of the elliptic arc, typically solutions have some kind of root-like pole, so derivatives might be infinite. That's something which is well known from sonic booms. Transonic flow models give rise to similar kinds of mixed-type partial differential equations. And the sonic boom is just this pole here, so one of the endpoints of the corresponding characteristic problem. So in cosmology, we have a cosmic boom, probably, in the setting, which isn't, it's some kind of divergence. It's much weaker than the usual singularities because it's just at this one point here, and these are isolated poles. Just for derivatives of these functions, which means curvature might still be infinite at this point, but not everything is infinite. So it's not necessarily a big problem, but at least it means that one has to be careful with the cosmological perturbation theory. If some poles show up, then probably the equations which have been derived perturbatively are not very reliable at this one point, at least, or it's in a neighborhood. Similar equations have been derived in strictly symmetric models where they do not require cosmological perturbation theory, so these poles are no problem in this context, but there are other issues. So that's my last example, related to non-singular black hole models. So the old ideas were that the singularity is replaced by a high density region, and we can use simple models in which the interior is homogeneous, evolve through the singularity and then somehow connect it back to the strictly symmetric outside. So if everything is deterministic in this high curvature region, that's a valid picture, would still have to be made consistent with the inhomogeneous exterior. But now there's an additional question, because also in these strictly symmetric models, the high curvature region is Euclidean, which means you would have to use some more complicated mixed type problem, which includes some future data in this Euclidean core. So again, not fully deterministic, and so that means if we start with initial values at past null infinity, they do not uniquely determine the future, because we can always evolve deterministically outside of this high curvature region, but not through it. So in the language of relativity, there's a new Cauchy horizon, because this whatever is to the left of this line C here and to the top of this hash region is not fully determined by initial values. So we still have an event horizon. Initially, the hope was that the event horizon is eliminated, because if there's deterministic evolution, we could evolve back from future null infinity. But also that is impossible. So the event horizon is back, and it comes along with the Cauchy horizon, which indicates that there are some global issues and problem of indeterministic evolution. So instead of a no-hair theorem, there's a no-air theorem, because without deterministic evolution, sometimes people use this for baby universe models through black holes, but the baby universes would not be able to inherit much from the progenitor universe if there's no deterministic evolution. So I conclude. So there's an effective framework for these canonical theories. In new quantum gravity, certainly it has been applied to models, so a lot remains to be worked out to understand the full theory. But the models have already highlighted some issues, most of them related to the anomaly problem. And signature change is usually the most characteristic one. So just to summarize the previous slides, if we use an evolution picture, there are instabilities, which means solutions are sensitive to initial data, but in this context also to all kinds of choices we have to make to get a good set of equations of motion. There are usually lots of quantization ambiguities. And combined with instabilities, that's usually a very dangerous situation, because it is hard to see how predictions based on a single set of equations of motion can be made more reliable. So one would have to switch to a mixed type problem to get rid of instabilities, but then one also loses deterministic evolution. And that gives rise to all kinds of additional global problems, Cauchy horizons, and some of these poles, which means that perturbation theory, in homogeneity at least, may not be so good anymore. So the framework has raised some questions. They still have to be addressed. We don't really know a lot about the solution space, so it's hard to say at this stage what these global problems mean. But at least one can say something about solutions in more concrete terms, and that will hopefully tell us how we can evaluate the theory in meaningful ways. So I stop here, and thank you for your attention.
So I want to understand what happens in the case if I don't go to, let's say, full quantum gravity, but I take some other system, a reparameterization invariant system, where I could maybe do your trick that you did in the Friedman equation and do this deformation that involves, let's say, sign deformations or things like that, right?
Yeah.
Is there sort of a toy model where one could understand this without going to sort of full-blown problems of quantum gravity? Something particle-like or string-like, whatever, give me 0 + 1 or 1 + 1, where I could sort of see some of this issue, and in particular the signature change, what that would mean.
Yeah, there are some models. I mean, these spherically symmetric models are simple models in which you can see it and which do not require an expansion of inhomogeneity. Another setting would be there's some scalar field theories developed by Vicar Hussain, Sanjeev Siara, Ghulam Hussain, and others. And so they use a scalar field theory on a standard background space-time, but they modify the kinetic part in a very similar way. And they recently had a paper about dispersion relations, which I haven't had time to look at the details yet, but there should probably be similar features. So yeah, these scalar models, you could do them in 1 + 1, 3 + 1s, and you would see signature change in all cases. So yeah. Right. That's just another way of saying there are instabilities with initial value problems. That's true. So in this case, we do not have to re-quantize the theory necessarily. It's an effective theory of something which has already been quantized. So in that case, at least, ghosts are not such a big problem. But the corresponding instabilities still appear at the level of effective equations. And one can eliminate them by using these mixed type problems, but then you get into indeterminism. So it's certainly a set of questions related to it. Maybe one other remark in this context. So this Euclidean theory we have is not standard Euclidean quantum field theory, because there's no Wick rotation in this case. So usually the Wick rotation would change the sign back to what you need to eliminate ghosts, but that doesn't happen here. So, or maybe one could somehow reintroduce it for some other reason, and it doesn't come from this holonomy modification to get rid of ghosts or other problems. But it's right now it's hard to see why you should use complex coordinates.
So at some point you mentioned that in gravity is kind of different from gauge theories because fixing the gauge and working in gauge-invariant variables can lead to different results. Do you know any example of that?
Well, this is an example. I didn't really emphasize it very much, but if you could use this this bounce background and just use equations for inhomogeneity in some gauge fixing, and just quantize them on this background here, and you would not have any. You would not see signature change. You would not have any problems of indeterminism through the bounds. So that's very different from what you get if you try to first embed this into a non-gauge fixed inhomogeneous setting, then quantize it or compute effective equations for it, and try to evolve. So that's the main example I know. I guess it's always, gauge fixing is never unique, so there might be a gauge fixing which would be the right choice. But then different gauge fixings may not lead to the same results. Because in this case, in contrast to standard QFTs, it's a very complicated gauge system. QFTs which are usually, in which we understand well, if you have a Gauss constraint, it's not really so difficult to show that different gauge fixings lead to the same results. But in this case, with structure functions and so on, we don't really know very much about these systems in general terms. So, and then it is much more complicated, and different gauge fixings can often lead to inequivalent results.
But
Yeah, well, that's is only with these holonomy modifications. If you do not use them, you do not get signature change, and you do not get this inequivalence.
I guess there's a simple answer for that. It's any system which has an anomaly. So, you know, you can gauge fix classically, but and if it has an anomaly, you won't see it after you quantize. So what it's doing is, you know, the question is whether the diffeo algebra has an anomaly or not. That's the big problem in quantum gravity.
Well, there's no anomaly here, so that's still a closed set of generators.
But it's a modification. It's not an anomaly, but in the sense it's a modification of the algebra that you
right,
don't,
because you have quantum corrections in your gauge structure.
But more generically, yeah, let's talk about the anomaly, because the big problem here, you talk about this, I don't know, you only have one constraint. So in some sense, you will never really generate anomaly. But if you usually modify arbitrarily the Hamiltonian constraints by, you know, nonlinear terms, you're going to, you know, generate anomalies, which means that even, you know, you will not even be able to write down a closed algebra there. So your analysis is valid only for this simple homogeneous model, right?
No, not this one. So that's, there are two cases here. So one is perturbative inhomogeneity around an isotropic model. But you make sure that the inhomogeneous constraints, which have a non-trivial algebra, so really this one with beta equal to 1, are modified by these higher order terms so that you still have a closed algebra. So it's certainly not, you do not just arbitrarily modify the constraint. It turns out that this f function here is still free, but then, where was it? It's, yeah, the sine function here, for instance. That's still free, but anything which you have in higher order terms has to be related to this function in a very detailed way. So that's been worked out in these papers. And then you get a closed set of constraints with this algebra. So the right-hand side is really non-zero, which allows you to read off this modified coefficient beta. The second case is spherically symmetric models, which are not homogeneous. So you still have variations in the radial direction. And you get a closed algebra, closed brackets like this, again, with the same kind of modification.
It's not some kind of Filter definition in disguise?
In some cases it is, but if it's only a redefinition, you would not get signature change. It's really an inequivalent kind of space-time structure derived from the constraints canonically.